So hello, everybody again. This is the last talk before lunch, the last talk of the morning session. And we are happy to have with us online Khudoyor Mamayusupov from the University of Uzbekistan, who is going to talk on generating holomorphic functions with critical orbit relation. Thanks very much.
Thank you. Thank you, organizers, for giving opportunity. It's a pleasure to talk here. So I will talk about generating holomorphic functions with critical orbit relation. So it's joint work, so work in progress. Joint work with Mark Khudoyor and Khudoyor Mamayusupov. So yeah, so the iterate of function we denote by like this. So have little o(n). So consider pair 1 lambda, the set of conformal conjugate class of quadratic map in modular space of M2. So it has each map of in this family has 6 points with multiplier lambda. For lambda 0, we just consider the quadratic polynomial family. So in 2015, the Markov, Wang, and Ye proved that pair 1 lambda contains infinitely many critical finite maps if and only if lambda is 0. In other words, if you take this not the lambda not equal to 0, you cannot have infinitely many post-critical maps. So map is called post-critical finite. If every critical point has finite orbit. By orbit, I mean the forward iterate. So, but in MD, so in rational maps of degree D, the modular space, post-critical maps form very evident subset by the above result of Laura and their colleagues. Some subvarieties in MD are special. So now consider this family where Laura and their colleagues consider. So F sub TZ is this family for every lambda, and T is here parameter. So lambda non-zero, of course, and it has 2 critical points at plus minus 1. So we mark them. So we know this mark space by pair 1 lambda Tm, which is double cover of pair 1 lambda. So the main result is the following. So for H lambda non-zero, which is the complement of or the negative part of Laura's result, which is lambda is not a root of unity. In the family, all critical orbit relations are realized except the 0, 0, and 1 for Hn. So here the condition on lambda not being root of unity is technical and avoid, and the result still valid. So consider rational functions, holomorphic family of rational functions.
I'm really sorry, but you that was a little bit quick. I didn't really have time to take in the results. So this is your family pair 1 lambda Cm. So this is basically pair 1 of lambda.
Yes.
And you're saying that in this family you can find all critical orbit relations. So your notation for critical orbit relation means
so you have 1. So you have plus minus 1. So you iterate plus 1 some number of times.
Yes.
And then you reach iterate of minus 1 on the way.
Okay. So the number
I don't
of times...
consider in the case of post-critical finiteness, I don't consider only one critical. It will come.
So your two numbers. Sorry.
Yeah, here
sorry.
is definition.
Yeah.
Yes.
Okay. All right.
I consider distinct critical points. Yes. So
okay. So this is the definition. Thank you.
Yes. So we have 2 critical points. We don't need to mark them actually. So critical relation is a pair, or if you want to specify the point on the parameter plane, then it's a triple of non-negative numbers, and M. Let's say for the 2 critical points, we have this relation. So on the left, I iterate 1 critical point some number of times, and on the right, I iterate another critical point for another number of times. So I allow 0, 0. In this case, those critical points can collide. It's also fine. So let's mark now critical points. We have 2D minus 2 critical points. So in order to mark them, we pass through branch power. So as the conference title, there is a Juliet set. So I have to justify my talk. So I say T equals T naught belongs to stability logs if the Juliet set moves holomorphically in the neighborhood of T naught. Or alternative definition is by normal family. You take your critical points, you iterate by your function, you obtain sequence of holomorphic functions. This is a family for normal family for HI, for H critical point. Then the point belongs to stability logs. If it fails, then it's called bifurcation. So they belong to bifurcation logs. So now setup for my setting, yeah. So I assume that bifurcation locus is not empty, and I have some critical point which has non-exceptional, not exceptional, but it means that orbit travels somewhere, goes like as orbit of at least 3, length 3, or infinite, and it persists throughout the parameter plane. And you have another active critical point. So you take from the bifurcation point some parameter. Then the following is generalization of analogous results for post-critical finite maps. And there are infinitely many parameters such that Ti and that Tj have critical orbit relations. Well, proof is just followed from Montel's theorem. Well, in fact, we can say more. We can have infinitely many parameters T and corresponding N, such that the active critical point iterate N times lands at Tj. For this, you just apply Montel again for this case. Well, if you cannot have two preimages, distinct preimages, then you are already done, because one preimage is critical point, then it lands in one iterate to another. Okay. So for introduction of the method, I consider specific families with two. Well, I say active, but we don't need active. We need at least one active critical point. So I consider this cubic polynomial family and the pair 1 lambda. And also, so in these two families, I will reach some kind of equalities, and I give that in for general setting for polynomials and for rational functions. So, and then also, so actually the motivation to study this comes from this family, or from pair 1, 1 as well. So this maps, this critical relation not only come from bifurcation locus, but also come from stable components. Whenever you study or parameterize stable components, you have two critical points having some relations, then you cannot destroy them, they are there. So you have to have some control on them. So let's consider cubic maps. So this is in Brunner-Hubbard normal form. We have marked two critical points plus minus a. And two distinct cubics are conjugate via z goes to minus z, and only if d is, so the d prime is minus d and a prime minus a. So I take this in this form because it interchanges the critical points. So modular space you can consider, then you can take coordinates like a square and b square. Then critical order relation is just this one, because you can have either of the cases. So we can consider two cases, like you can have like n n and m be minimal. Minimal means if the first one from this product is 0, then all the lower level iterates should be distinct. Otherwise, you reach earlier, then you don't call it like higher order orbital relation, but some lower order. So by this definition, if you have n0, then it's minimal. So previous for the previous lemma, so this kind of relations are infinite. Yes, because of the symmetry, it's enough to consider n bigger than equal m. So now we are interested in finding all such cubic polynomials.
Excuse me, Khudoyor.
Yes.
So you allow that n minus i's and m minus j's iterates coincide for different ij?
Yes.
I see. Okay.
Yes. So I classify all of them. So I give all of them some iterative procedure. So the problem for finding this may be computed like directly by computing resultants of these two polynomials, or you can also try to find Grobner bases. So for like if you want to do it on software like symbol software, you can do this kind of experiment, but it's very slow. So here is a key lemma behind the key idea. So there are sequence a and bn of two parameters, such that if your critical point is z, then all iterates can be a affine function of this z. Well, it's not so difficult. Define this map. They are defined such that the previous one you plug it into p, your function, your cubic polynomial, you obtain another one. So the key idea is here. So your critical point solves some quadratic equation. So you can always reduce the powers. So for instance, z squared is just a square. If you consider a as parameter, then you exclude it. So higher degrees also get reduced. So from the relation, yeah, and then you just expand this. You get z cube. You replace by a square and z. You combine common terms, and you have your this recurrent relation. So this you can also read the degrees of an and bn. So a is dominant here. So degree of an is 3 to the power n minus 1, and degree of bn is 3n minus 3. Yes, to a. So yeah, this a and bn have some nice form. So for instance, an is polynomial of actual a squared, b squared. So they read the modulus space, and bn is factor of b, and what's left is again polynomial of a square and b square. So main result, so except 1, 1, all critical relations are realized. In particular, there are infinitely many cubic polynomials with critical orbital relations. So actually, this means there are curves of them. We'll see them in a moment. So now I give the proof. So for the case of n, so by our key lemma, we can easily get the critical order equation. So we don't consider 0 or 0, we consider for other case, then an should be 0. If you have the same level n for the orbit for the critical relation, then it's just an equals 0. So let's try to compute the first one, a1. Well, a1 easily you can compute minus 2a squared, so it vanishes with a0. But a0 means minus a is also 0, so our critical orbital relation is actually 0, 0. So we don't have 1, 1. Well, this means no critical, no cubic polynomial is orbital relation 1. And we can explicitly find the polynomial like we take an, cancel by a1, which is not 0, and define this p and n. When p and n is 0, then n critical relation is realized, and define tilde. So take the previous one, so plug it in here, the recurrence relation for an. What's left here, defined by tilde, then you have the following product formula. Or the, here, or you can use the property that a and b and are polynomials of a squared b squared. You have you can write a different form. So you have this factorization in some sense. So here is the proposition which reads the degrees of this where we can say curves. Yeah, when they are 0, then you have critical relations. But if you want like minimal critical relation or exact critical relation, then you have p tilde. One remark here is that, yeah, look at here, for instance, they can intersect with each other, so it's not like ideal. Well, they intersect at finite many points. So for the generic choice of B, for instance, you have distinct. So if you fix B, then it's the polynomial of A. Then this points. So this factorization will be like without any common factors. So for the case of n and 0, n and 1, it becomes a little bit harder. So you get this kind of or you get like solving on the third line. Here, critical orbit relation is realized, then this is 0. Then you plug it in of z plus minus a, you get the bottom line. You have a polynomial p sub n m. And we can easily compute, for instance, for m equals 0 and 1. We have explicit formulas for them. And we have this factorization. So what's remarkable here is that this formula, so the n1 is factored by n minus 1, 0, and then the true relation or exact relation n1. And it's always, it appears with square, so it's squared. And here is degree count, so degree of p n not tilde is twice the degree of 2 times 3 to the power n. And for the other case, also I have a formula. I don't need to spend time for it. And we can also denote them by Q. Q will appear in modular space. So I introduce them here. And we also know explicitly the formula for the degrees. So in summary, all 3 cases are considered above, and the 0 level set of this p tilde corresponds to exactly an m critical orbit relation. And we can consider this set, crit and m, for parameters a and b, such that p tilde is 0. And we can say that except 1, 1, all critical orbit relations are realized, and there are infinite many, there are curves actually. And for modular space, we can also say that if you take coordinate a squared b squared, then exact or minimal critical relation corresponds to Q's being 0, and it's never empty except 1, 1. And now we can consider these curves where Q and n is 0, those affine algebraic curves is analogous to curves defined by Milnor for the study of cubic polynomials. So for the Milnor's case, you have plus a or minus a, which is prefixed. So eventually, pre-periodic. Eventually, it creates orbital geometry itself. And here are some examples of these curves. For instance, S00, S10, S20, and S22 are like these are graphs of polynomials, so they can be identified by complex plane. And we can also know the degree of these curves, which are half of the degree of this polynomial. And here is a degree table of these curves. And now I would like to show some variety in this cubic polynomial family. So just take here 1, 1. And here 2 dots represent orbital relation 0, 0, which is exactly A being plus minus square root of 3. And then so now I add more and more iterates. Now it's 1, 0 iterate, it's also added, and 2, 0. Well, 1, 1 is never that, is empty, so I skip that. And 2, 1 is added to the previous data, and so forth. I keep adding, I get more and more. From here, you can also see some kind of, so this is cubic family. You have like 2 butterfly wings, where you have 3 critical points, which is in the immediate basin of parabolic fixed points. So this parameter space, all functions have parabolic fixed point at origin. And these 2 landscapes, they have attracting fixed points and 3 critical points in the basin of that one. So I keep adding more and more. I get more and more dots. So this is conference is number 4. So I stop at 4. Well, now I also did some more experiments and just took 6, 0. And here is red dot represents. This is just 6, 0. And also I take 6, 5, for instance. For 6, 5, you see more inside the stable component. Actually, here for the previous one, for 6, 0, you have 730 points. So it's the degree. And for 6, 5, you have 648 dots. Now for the space per 1 lambda. So it has plus minus 1 critical point, and it has critical relation below. And again, so the key lemma, so it is iterates are like a quotient of 2 polynomials. So if for each polynomial, we can use the previous idea. So here is 4 sequence of functions, so polynomials. And we have similar results. And for instance, so here dominating term is D, and the leading term of D can be computed, as you can see from here, the roots of unity here. So this is why this is excluded. But if it is roots of unity, then degree will be a little lower, but still you can compute them. And the main result is here. If lambda is not a root of unity and fixed, then in this family, parameters by T, all critical relations are realized except 0, 0 and 1, n and 1 for each n. Yeah, these are not possible. So define P and M as previously. So I don't want to stop here. And we explicitly know the tilde for the case of n, and we have this factorization. And we know the degrees. So n relation is minimal, then tilde is 0, and we can also see 1, 1 is not realized here, and we have this factorization. And for the case of n0 and n1, we have, as I said, we have this proposition. So it's it's the next one divides the square of the previous one. And here we don't have other factor than lambda square. So this is why n and 1 or n plus 1 and 1 are never realized. Never possible. So for the other case, also I have explicit formulas, and degree count here comes from the leading terms are d. So degrees of double the degrees of some of the degrees of d. So again, I can factor them. And now the idea why we have this kind of squares on this on this proposition comes. Well, this is true for generic holomorphic functions. You have critical value. The function is square of argument. For the polynomials, we can explicitly compute those coordinates. So since you write Taylor formula for your polynomial at the critical point, actually you don't need to put them into plus minus 1. You can have like somehow if you have two critical points, they solve some quadratic equation. You change coordinates, and you can also put them into some rational function of some parameter. Here we see that fz minus p1 is multiple of z minus 1 square. Now plug it in instead of z, iterates of the other critical point. Then you get this second line where you can explicitly compute g1, which is polynomial, and you do the same for the other, and you multiply them, and you get n1 iterate or n1 critical relation and n minus 1 0 relations are related to each other, and the other factor is g1 times g2. So you define tilde by the product. So if you have explicit or the minimal relation, then g1 times g2 should be 0. And for cubic polynomial, it's easy to compute, and it coincides with the previous result. And now for the same idea works for rational functions. Here you take Taylor development. Actually, this is g1 and g2 here. Again, rational function. You can also compute it if you need. And again, that relation is g1 times g2. And now for the remaining time, so here is the cubic rational family. So it has 0 and infinity super-attracting fixed points, and there is another 2 fixed points. They're colliding. They create one parabolic fixed point with multiplier 1, and conjugate is 1 over z. They conjugate a and minus a. So we consider parameters, non-zero parameters. So 0 is excluded because if you consider 0, you get z squared, so it's degenerate point. Again, we study critical relations, but here our critical relations solve this quadratic equation. Minus 1 is excluded. So now we can do the same method. We try to find this sequence, but it becomes really huge. Yeah, here they are. And also some experiments. So this is work in progress. So these are like open problems. HAN, BN, CN, DN are factors of A, and only CN and DN factors of A plus 1. And we know the degrees, and also we know the leading coefficients, they are recurrent. They're given by recurrent relation. And also we explicitly know NM critical relation. Yeah, we are lucky, we know, even though it's huge. And also we know NN. NN is simpler. Here again, well, it is would-be theorem. All relations, all critical relations are realized except 1, 1. Well, there is a topological reason why 1, 1 cannot be realized. And also for NN, we know the tilde. It's also good. Well, there is continuation. And also, we have this factorization for NN, and we know the degrees. Well, there is a computational reason why one is not realizable. Well, this a square times a square plus 8 is actually the discriminant of the critical point equation. When it's 0, then points collide, the critical points collide. So then it is 0, 0 relation. And we have this factorization similarly. And for cases also, I know exactly the factors, but I don't know for the other cases because reason is it's like huge formula. If you substitute, there are like 8 parameters. So for instance, in Mathematica, it gave me like 14,000 symbols, the only formula. So here are some examples of those polynomials. And the degrees up to 6 are given here. So this table coincides with the table of pair 1 lambda, which is well, it's not so surprising. And there I was showing you up to level 4, and then 6, 0 and 6, 5 here. Well, in summary, we have this would-be proposition about the degrees. And here is a parameter space. Well, these are also similar. These butterfly wings are here as well. And you have two landscapes. Here they are green and blue, which correspond to super attraction. So when three critical point lands in the immediate or is in the immediate basin of 0 and infinity. Some open problems. So this we have a lot of polynomials, and we would like to know whether they are irreducible. So experiments show they are. And another good research would be distribution of this critical rotation in bifurcation locus. And here I stop. Thank you very much.
Thank you very much, Khudoyor. Thanks for the very nice talk. And are there any questions or comments in the room?
Sorry, could you go back to your family of cubic polynomials? I don't think I quite caught which slice of cubic polynomials you were looking at.
Cubic polynomial.
Yeah, you had cubic polynomials right at the beginning, the first when you were talking about finding these relations. All right. So sorry. Yes. So that was the one z cube plus a. Is
yes,
this one?
Here.
Okay. So
yes.
so what is the so what is it that defines this? Oh, sorry. So you've got two.
Yes.
Well, you're looking at you were looking at a one-dimensional slice, right? In order to find critical relations.
No. Just two parameters.
Yes. You're looking at the full family of cubic polynomials.
The curves are also like in T2 Riemann surfaces.
Okay, but so presumably, I mean, if I was to find the critical relations of cubic polynomials, I guess I would draw I would kind of try to draw a Hubbard tree and use Thurston's theorem. So are you saying that by looking at doing these algebraic considerations,
yes,
you don't need
to study.
You don't need to use Thurston's theorem. Is that what you're saying?
Well, for classification, you may use Thurston's theorem, but if you want to do like kind of experiments and see the combinatorics, you can also recover them from this procedure. Yeah.
Okay. All right. Thank you.
Any further questions, comments? The people online, maybe?
I have a question. So later you have a picture for cubic polynomials with one parameter.
Yes.
So here you have just collections of points where you have critical orbit relations.
Yeah.
So when say you fix m equal to 0, n goes to infinity, or when n, m go to infinity together, do you have some ideas what will you have in the limit for the set of these points? I mean, based on the picture, it seems like
yeah. Of
it
course,
approaches
the
bifurcation.
degree, yeah, degree is like exponential. So when n and n grows, then your points grow exponentially. And basically, what you see is that let me show the 6, 0 here. So here, basically this is the hope. Yeah, they will equidistribute on this, but maybe this is not correct way of saying it. There might be some, as you can see, that this limit case is like kind of has almost no point. Yeah? But here butterfly wings has a lot. They will at least they accumulate on these butterfly wings. Maybe they also accumulate like they distribute on this limit case as well. I don't know. Yeah, this is what we expect when your n is huge. For instance, m is 0. But if m is also a lot, then of course you get like this picture. You don't see a lot of points in this interior, but most of them will accumulate on this near these boundaries. There is a bifurcation. This is what you see in the limit. Did I answer your question?
Yes, thank you.
Are there any further questions or comments? Anyone online? Okay, if not, then let's thank Khudoyor again for the very interesting talk.
Thank you.
And I believe there is a lunch break now.
So I stop sharing.